Welcome to Study Life. In this session of semiconductors and electronic devices, we are going to learn about the energy bands of P-type and N-type semiconductor. Let's go down to this very detail that we learned in our very first videos. We studied that if I draw the energy bands, this happens to be my valence band. Over here at the top is my conduction band. This here is my energy gap, forbidden energy gap. We know all of this until now, right? We've learned that for metals, there is no forbidden energy gap. The valence band and conduction band kind of overlap. For insulators, the band gap is very huge. The band gap is very huge. No electron from the valence band can move into the conduction band. But for semiconductors, the band gap over here is around 1 electron volts to a maximum of 3 electron volts. And there is a huge possibility that under different conditions, an electron from the valence band can move into the conduction band and therefore conduct electricity. But when we talk about P-type semiconductor, P-type semiconductor is a type of semiconductor wherein we've created holes. This sort of P-type semiconductor has got some impurity. Those impurities are referred as acceptor impurities. Those impurities are called as acceptor impurities, and they have an energy level that is equal to, that is said as acceptor level. How do I draw this? If this is my valence band, this happens to be my conduction band, and let's say this is my energy gap, and assuming that this is equal to 1 electron volts. Simple. My acceptor level, the acceptor impurities brings in some acceptor electrons, and these acceptor electrons will have an acceptor level. This acceptor level is somewhere over here. It's somewhere over here. The difference between the acceptor level and the valence band is 0.01 electron volts. So now when there is an electron, it doesn't have to move from valence band to conduction band. It has to move from the acceptor level to the conduction band. That means the forbidden energy gap for a P-type semiconductor is kind of low. It is kind of low. So I suppose you've understood what happens with a P-type semiconductor and the energy bands related to it. Now let's work on an N-type semiconductor. Let me draw the energy band for my very pyara N-type semiconductor. Let's do this. This over here is my valence band. This over here is my conduction band. Over here, I understand there is an energy gap that is approximately equal to 1 electron volts. Happy. N-type semiconductor will have some impurity that kind of donates electrons to this entire scenario, right? Since it's about a donation, the impurities are called as donor impurities. The impurities are called as donor impurities. And this type of semiconductor is called as donor type semiconductor. Okay? What happens over here is there's an energy level that is created over here. This is called as donor level. The energy gap that this donor level over here creates is equal to ED 0.01 electron volts. So now when I talk about an electron, my electron has to move from the valence band into this donor level. It doesn't have to go towards the conduction band. It need not go reach the conduction band. It can stay at the donor level and then conduct electricity. Simple, very basic, easy. Don't you understand that due to the addition of the acceptor and the donor impurity, my energy gap has reduced a bit. In here, it was from valence band to conduction band. Now it is from donor level to, acceptor level to conduction band. In here, it was from valence band to conduction band, but over here, it is from valence band to donor level. The things have been simplified only by addition of small impurities. So now I suppose everybody has understood what happens with the energy bands, and then we'll start with our next topic with the next video. Until then, stay tuned with Study Life.